Good afternoon, everybody. Thank you for joining us for this unique webinar. I'm Lynn Rubenstein, and I'm the Executive Director of the Northeast Recycling Council. This webinar is being co-sponsored by NERC in collaboration with the Association of Plastic Recyclers, APR. This webinar is being recorded. Both the recording and the PowerPoint presentations will be posted on the NERC website, and you will be sent the links. So we got a lot of questions about that. So just the answer is yes and yes. In a few moments, I'll introduce our speakers, but first I want to explain how you'll be able to ask questions, which we most definitely want. I'll be asking the questions to the panelists at the end, but please be submitting them while you're thinking about it. So if you're not familiar with the GoToWebinar dashboard, on the upper right hand of your screen, there is a little orange box with an arrow. You click on the arrow, and that opens up the GoToWebinar dashboard. Towards the bottom of that, there is a question box. So you type your question there and hit return. I'm the only one who's going to be seeing them, and I'll be monitoring the questions as they come in, and we'll ask them at the end of all the presentations. I'd also like to call your attention also in the dashboard that there is a document, a PDF that you can download. It's a fact sheet about using drainage pipes with recycled content. That too will be available to you after the webinar, but I just wanted to let you know that it's available to download now under handouts. So with that, I'd like to introduce our speakers. The first speaker will be Liz Bedard. She has over 40 years experience in the solid waste management recycling field. She was the director of the New Hampshire Governor's Recycling Program and a founder and twice executive director of the Northeast Recovery Association, the country's oldest and largest recycling cooperative. Currently, she is APR's Olefin Rigids Director and Senior Director of Industry Collaboration for the Recycling Partnership. Liz will be followed by Dr. Plumier. He is an associate professor in the Civil Engineering and Applied Material Sciences departments at the University of Minnesota in Duluth, Minnesota. He obtained his PhD in civil engineering from Villanova University and also has a master's degree in mechanical engineering from the University of Minnesota. His PhD research was on the performance of corrugated HDPE pipes manufactured with post-consumer recycled content in commuter railroad applications. He is also the co-principal investigator of the field performance of corrugated HDPE pipes manufactured with recycled materials, which was published by the NCHRP and resulted in the changes to the AASHTO M294 that we're going to be discussing today. Following Dr. Plumier will be Ryan Fragapane. He graduated from Mercyhurst University with a bachelor's degree in biology and a minor in sustainability. He has been with AASHTO for 6 years, working in various roles. He is currently the Associate Program Manager of the NTPEP and oversees all of its manufacturing audits for various products. And finally, but as we say, not least, we'll hear from Joe Babcanec. He is currently National Engineering Program Manager at Advanced Drainage Systems in Hilliard, Ohio, and has worked in design and new product development for ADS since 2005. Prior to working for ADS, he received a BS in Civil Engineering from Ohio University. He is a registered professional engineer in the state of Ohio and has served as a member of the TRB Committee on Culverts and Hydraulic Structures and ASTM committees on plastic piping systems and concrete pipes. So we have a phenomenal group of speakers today. And with that, Liz, I'm going to ask you to give us your opening remarks, and thank you.
All right, Lynn. Thank you. Lynn, are you able to see my screen?
Absolutely.
All right. Well, let's get started. Good afternoon, everyone. It's a pleasure to be here, and I would like to kick off by thanking NERC, the Northeast Recycling Council, and in particular, Lynn, for making this webinar possible. I'd also like to thank all of you that are here listening in and here to learn about this subject. Please don't underestimate the importance of this topic. This is an important component to stable, sustainable domestic recycling. And so I'm so pleased to see so many of you here to learn about it and all of us move this forward together. So let me start off with, if I'm able, who APR is. APR is the trade association for all things plastic recycling. Think about anything that would have to do with plastic recycling. Recyclers, equipment dealers, brand name companies because they want their products recycled, resin producers. We really are there to move recycling forward in a successful, sustainable way. And we do that through 4 areas. Our primary goals are to increase supply, so get as much plastic recycled as possible, enhance quality. You know, recyclables are our feedstock for manufacturing, so the quality of the recyclables are very important. Expand demand. Think about the chasing arrows. We need demand for that which we pick up at the curb, so expand demand. And then communicate the value of plastic recycling. And today, we're talking about expanding demand. So this really touches upon APR's work around demand. And why is this particularly important now? Well, the state of plastic recycling today. And to tell you the truth, I'm always surprised at how deep this situation that we're in right now with recycling has been communicated to people so much outside of recycling. I'll be almost anywhere, the grocery store, and when someone hears that I'm involved with recycling, they'll say, gee, I'm so sorry to hear about China. Oh dear, is recycling falling apart? Well, we do have a perfect storm. We are in transition. We do have issues, and I've outlined a few of them here. 65% of the curbside collected polypropylene was exported, and almost all of our bulky rigids. So think about 5-gallon buckets, that kind of bulky plastic. Also, we have what I call a virgin resin tsunami about to hit the marketplace, an estimated 8 billion pounds. And then this idea that we don't have major commitments for recycled products. So can you imagine being a company where you have a standing order for 20 trailer loads a month of your product, and it can be just instantly canceled because we don't have a lot of long-term commitment to recycling? And you know, I want to spend a couple of minutes on this, what I call the tsunami of wide-spec virgin resin entering the marketplace. 50 million pounds to 160 railroad cars per month of this material is going to hit the marketplace. This is often because of the natural gas. So we're seeing a lot of virgin material being produced. And this is in direct competition with recycled material. And this is economics 101. The more supply that's out there, and if we don't increase demand, then prices go down. And that's just one more difficulty for recycling. And for residential plastic recycling to be sustainable, there must be sustainable plastic recycling markets. Think of the chasing arrows. Think of maybe one arrow being the material picked up, the second arrow is the material being processed. But if we do not have the third arrow, if we do not have markets for these recyclables that we're picking up, then the chain is broken and the system falls apart and it is not sustainable. And can we continue picking material up at the curb if we don't have sustainable, and I'm going to say domestic markets? I think what's happened with us putting all our eggs in one basket for certain plastics and exporting them was a weakness in our system. And we're trying to correct that. So the APR Recycling Demand Champions is a program that is creating demand for recycled plastics. Demand creates value, value drives recycling. And really that gets us to what we're all about today. And that is that 6 months ago, I was so pleased to discover that the new AASHTO specs allowed for plastic pipe products to contain PCR, post-consumer resin. And that just changed things. And that's why we're here today, is to talk about that, learn about that, discover how we can have this make a difference with domestic plastic recycling. Have this make our domestic recycling stronger, help this ensure that the plastics that get picked up at my home, the plastics that get picked up at your home are going to continue to get picked up. So APR has partnered with the Northeast Recycling Council, NERC, on a multifaceted plan. And this is part of it. You see that I've highlighted webinars. But they're going to do a number of things that I hope that many of you that are on this webinar today can access, can help you get involved in having more infrastructure pipe be used that contains PCR. There'll be a manufacturer's directory, case studies, overview material. We'll be educating as much as we can via this webinar. We'll be working with DOTs in the NERC region that haven't yet approved AASHTO, and as importantly, measuring the impact of the project. So with that, I'd like to close off my comments because we have a lot of important information to hear, and I'll pass it back to you, Lynn.
Great. Terrific, Liz. Could you please pass it to Michael Plumier?
I will.
Thank you.
Hopefully I've successfully done that.
Oh, you have. Michael, yay. Now we just need, what's it called, slideshow, and it'll be perfect. Thank you.
Okay, thank you very much. I have a number of slides to go through, and so I'll go through some of these fairly quickly. So there will be some question and answer time at the end of this webinar, I've been told, so I'd welcome any comments or questions at the end as well. But I apologize if some of these are a little bit technical in nature, too technical in nature, but hopefully I can speak to a broad audience here and make this material pretty understandable with regards to what we actually did and what we accomplished in our research. So basically what I'm going to go through is the thrust of the research project that led to this change that Liz had mentioned in the AASHTO standards for corrugated pipes. And if I can get to the next. So I'm going to go over quickly our research objectives, talk about corrugated HDPE pipe for those of you that may not be familiar with the product, talk about really what was the thrust of this research with regards to service life, because if we're going to make any change to a specification, we want to make sure that the change is not going to hurt or adversely impact the service life of the pipes used for our infrastructure applications, and then I'm going to talk about the results of the research. So the main research objectives were to evaluate the viability of incorporating both post-consumer and post-industrial recycled materials into these pipes. We focused largely on post-consumer recycled materials, and I'll talk a little bit about that in a moment. And we wanted to determine the effects of these materials on the service life and durability of pipes, and then develop a specification that would allow these products, if the research deemed it appropriate, to be used in these applications in highways and underneath railroads. So there were three primary sponsors, research sponsors for this work. NCHRP is the National Cooperative Highway Research Program, and it's basically a state-funded program. So states pool money together for projects that they're interested in, research that they're interested in, and then it gets voted on with regards to which projects actually get funded. And there was a number of states that had an interest in using more sustainable materials for their infrastructure applications, and therefore they funded a couple of large research projects that funded this work. So NCHRP Project 4-32 and 4-39 was a follow-up project to 4-32. And then also I'd like to make note that the Southeastern Pennsylvania Transit Authority sponsored some of my PhD dissertation work by further evaluating these pipes. So I'm going to talk about all three of these research projects. So corrugated pipes are typically used for storm sewers, culverts, other land drainage applications. They're manufactured in small diameters of 4 inches up to 5 feet in diameter. So these can get very, very large. So the pipes that are typically used in culverts underneath your roads are larger diameter pipes in the neighborhood of 12-inch to 60-inch diameter pipes. The 4-inch pipes are used for smaller drainage applications, either agricultural drainage or some of your edge drain applications on highways. These are attractive products just because they are very durable, they're resistant to corrosion and abrasion, and they can last a long, long time. So they have some some benefit with regards to that for our infrastructure applications. Traditionally, these pipes have been required to be manufactured with 100% virgin materials, and that's been in place as long as the standard was in practice, which is probably over 20 years. So for the last couple of decades or 3 decades or so, these pipes have been required to be produced with only virgin materials. We studied both post-industrial recycled materials and post-consumer recycled materials, and the standard now allows both of these types of materials to be used, either post-industrial or post-consumer. Post-industrial are those basically that have never reached an end user. There isn't a lot of these materials. There are some that are used in our applications, but by far the most dominant material for these applications are post-consumer recycled materials, which in this case are all polyethylene materials that we're looking for, and they are your laundry detergent bottles, milk bottles, things like this that are made out of polyethylene that can be reprocessed. And the picture on the upper right shows the washed flake material that is a post-consumer source, and then the picture on the lower right is that same exact material repelletized and formed into pellets. And those pellets are typically what we're using in the plastic pipes. We can use that flake material on the upper right picture directly, but the lower right picture is a more prevalent type of way of transmitting that material into the pipes. This is an image, and Joe Babcanec will probably talk a little bit more about this in his presentation, but I wanted to show just kind of, this is a image that was created by ADS, Advanced Drainage Systems, and their Green Line Polymers group. But it just is a real great graphic to show really what's the value here, what are we doing. And in this graphic we can see we're going from stage 1, where a consumer is putting his or her products out at the end of the curb to be recycled, and then at the end in image 10 there you can see those same materials eventually going in underneath as a storm drain in that same application. So you're taking a 1-year product in slide 1, maybe it's your Tide laundry detergent bottle, and you're turning that into something that's going to be in service, draining water in your underneath your roads and in your storm drains for in excess of 100 years. And so I think this image really depicts what we're trying to accomplish and the real value that we see in recycling. Now, some technical slides. There's a couple of interesting components with regards to polyethylene specifically. Polyethylene experiences 3 stages of failure: stage 1, 2, and 3. Stage 1 failures are ductile in nature. Those are under very, very high stresses. We can see that we're at a log stress on the y-axis and log time on the x-axis. Generally, for these types of pipes that we're dealing with, we don't see any stage 1 failures because these are non-pressure pipes under low stress. So we do not have these high stress failure concerns. However, our primary concern with regards to service life for these pipes is those stage 2 failures. Stage 2 failures will occur at low to moderate stresses and after a long period of time. And what we wanted to do is to make sure that period of time was in excess of 100 years for these applications. So we wanted to basically push that stage 2 failure curve out to the right to make sure we were in excess of 100 years. The stage 3 failures are chemical in nature, and those are generally just prevented by adding enough antioxidant or ultraviolet protection to the pipe to prevent UV degradation or oxidation of the pipes. And that's a pretty well understood mechanism that the industry has understood for a long time, and we're aware of how to ensure stage 3 failures do not occur. So the main thrust of our research was this stage 2. How can we make sure that that stage 2 failure curve is pushed out to the right far enough to ensure 100-year service life? So the way that this works, the stress cracking mechanism basically has been assessed historically in the corrugated pipe industry by doing these types of notched tests where we put a small notch in a test specimen. We put some constant stress or load on that specimen. We put that coupon, the dog bone specimen that you see there in the lower image, we put that coupon into some test bath at an elevated temperature to accelerate the failures, and then we wait for them to crack and fail. with recycled materials, we had to think a little bit differently because if we would do this same notched test for recycled materials, we're really not going to understand or find the effects of contaminants on that stress cracking mechanism. And so what we ended up doing was inventing a new test. Rather than the traditional notched test, we came up with a new test which is similar in design, but it involves testing unnotched specimens. And the reason for that, again, is so that when a specimen does fail or does crack, we wanted that crack to be initiated by a contaminant so that we could really understand the effects of these contaminants on the service life of these materials. So in the image on the upper right, we can see that the source of the crack in that specimen was a contaminant indicated by the bright area in the middle. Some contaminant caused this specimen to crack, and then the crack propagated right or left of that specimen, and eventually we saw ductile tearing on the end of the specimens. So the idea was to say, let's invent this new test method, and then let's try to relate that time to cracking to the service life of the product. So these are some images of contaminants that generate cracks in the specimen, and that was very typical of what we saw. So the way then we related that cracking time to service life is to conduct that test, that UCLS test as we called it, at least 3 different temperature stress conditions. And the reason we do that at 3 different conditions is you'll notice the equation, particularly the lower one, the rate process method, has 3 constants in it, A, B, and C. So the way we want to solve for those constants is to at least have 3 different equations. If we have 3 equations, we can solve for those 3 unknowns and determine the log T, which is the log of time to failure, as a function of stress and temperature. Alternatively, Poplar's shift method is similar in nature, but it involves basically biaxial shifting, where we shift the test data at elevated temperatures to more appropriate temperatures of which the pipe will be installed in service applications. So let me show you how this is done. So basically we would take testing at 3 different conditions, conditions 1, 2, and 3. Condition 1 was conducted at 80 degrees C, 650 psi stress in elevated water. The 80 degrees C is an elevated temperature water bath. Condition 2 is conducted at that same temperature, 80 degrees C, but at a lower stress of 450 psi. And condition 3 was conducted at 70 degrees C, a lower temperature, and at that same 650 psi stress as condition 1. The next thing we do is we apply those shift factors, the Poplar shift factors, a vertical shift factor and a horizontal shift factor. And those shift factors are simply functions of the temperature difference from your desired service temperature and your test temperature. And by doing those shift factors, we can then map a data point, shift that data point, if you will, to some service temperature. 23 degrees C is a fairly conservative assumption for the temperature of a pipe in a buried application, say in a state like Florida or one of the southern climates. In Minnesota, where I live, we're going to be shifting that even further to the right because it's going to be much, much cooler than 23 degrees in an in-ground condition. We can do that same shifting for the other 2 data points. And what we get is what we call a master curve. And that master curve is that same slope as that brittle curve that I showed you, those stage 2 curve that I showed you from earlier before. And this would be the prediction of how long this pipe or this material will last as a function of stress on the y-axis and time at 23 degrees C. If you wanted a different temperature, again, this curve would be shifted out to the right for lower temperatures, to the left for higher temperatures. We then established upper and lower confidence limits on that curve based on the scatter in the data. And we did this for 9 different full-scale pipes and actually dozens of other materials that we evaluated. But for example, pipe 4 was manufactured with 49% post-consumer recycled material and at a service stress of 500 psi, which is again a very conservative assumption for stress in these pipes. We would predict that pipe to last in excess of 234 years. If we looked at a pipe with 98% post-consumer recycled materials, we could see that that pipe would also last in excess of 110 years at a service stress of 500 psi and a service temperature of 23 degrees C. So this is encouraging. This is exciting. We felt that we had something workable here. The question was, though, right now we just have a model as to how long these pipes manufactured with different percentages of recycled materials would last. What we really wanted to do was evaluate and test that model. And one way to test that would be to install a pipe so that the stress was 500 psi on it and wait around for 110 years and see if we had failures. That didn't seem to be too attractive of an alternative, particularly for somebody like me that was trying to finish my PhD dissertation in a timely manner. So we needed to accelerate the test in order to validate, and we did this by two ways. One, in the laboratory, by installing some pipes under very, very high deflections, high stresses, much higher than what would ever be observed in the field. And then secondly, by doing the same thing in a simulated field test, as shown in the right picture, where we basically compress the pipes under very, very high loads with very poor backfill conditions to see how long they would last in that condition. This is just an image of our pressure cell that we compress the pipes in. Each of those concrete weights weighed 2,000 pounds. You see that there were 4 of them hanging on each chamber, and we had a 12-to-1 mechanical advantage with that loading mechanism, so we were generating in excess of 30 to 40 feet of fill on those pipes with a very poor backfill condition, so we were really stressing these pipes. This is some finite element modeling we did to assess how high the strains and stresses were in the pipe wall. And then basically we established some curves to come up with an average stress over the duration of the installed pipes. And we found that under these conditions, where if in that parallel plate test in the lab, we reached a stress of about 1,600 psi, which is again over 3 times what we had used for the service life prediction model. And in the buried pipes test, we made it to 1,528 psi. Then we can go back to these service life projection curves, and instead of projecting our failure time at 500 psi stress, we can go to that stress level, and we can create a failure window as to when that pipe would be expected to fail in the field due to brittle cracking. And so the 49% post-consumer recycled pipe would fail in a relatively short time, 1.4 to 3.2 years, still a little bit longer than was desirable for the purposes of our project. So that's why we had to manufacture some pipes with intentionally poor grades of materials to try to generate short failure times. And we did that on this pipe 3, which was projected to fail between 58 and 150 days. And what we found is that every single pipe that we predicted to crack within our predicted time frame did experience cracking within that time, and those that we did not predict to crack did not crack within our projected windows. So basically we went 9 for 9 on every single pipe that was tested. It matched our predicted results in the model. And this image shows one pipe with 98% post-consumer recycled material that generated cracks, and that crack happened to occur within days of when we had predicted it to occur. So we felt that the model was justified, and incidentally, I've spent about 20 years of my career working in the plastic pipe industry, and I can say that this is the only time in my 20 years that I was actually happy to see a pipe that cracked, because it really validated our model, and the model wouldn't have been, we would have had to start over with our basically from new if we were not able to validate this model. So that was a very exciting part of our research. So again, every pipe that was predicted to crack did. Those that were not predicted to crack did not. And basically, the beauty of this is that this is given us our first, what we call a performance-based standard for these products. Prior to this, there was never a performance-based standard for pipe materials, and now we actually have that. So that was very, very exciting. Note also that these are validation tests, and they're very extreme. They're not typical of actual installations, and the pipes were formulated with blends of materials designed to crack within a reasonable time frame. The final part of the presentation I want to discuss is a 3-year study we did with the pipes underneath railroads. And now these pipes have actually been in service for 6 years. And I'm just formulating a follow-up paper on the performance of these pipes after 6 years of service. But this was an interesting application because we wanted to see how well these pipes would perform in an actual application where it was very highly loaded. So we picked a railroad application, as the rail loads are typically higher than highway loads. And we went even beyond that, did a very aggressive rail application where we only had 2 feet of cover from the top of the pipe to the bottom of the railroad tracks. And the pipe on the left, the black one, is manufactured with virgin materials, and the pipe on the right is manufactured with recycled materials. And we coupled them end to end so that both pipes were seeing the same exact load from the railroad cars. We instrumented these pipes with strain gauges as well as string potentiometers to record deflections and strains in the pipe wall. We shut down the track for a day to do a complete installation. And then we monitored the loads in the pipes over time to see how they performed. And what we found is virtually no difference between the pipe manufactured with virgin material in the dark gray bars here versus the pipe manufactured with recycled material. They performed pretty much identically throughout the entire duration of the test. And we found that there was no difference in performance. So out of this, we were able to draft some revisions to the AASHTO specification to include recycled materials. In there, I do apologize, I have a slight typo. We have a 33-hour UCLS requirement. It's actually 34. There was a rounding issue on this slide, so I apologize for that. But that ballot was that standard was balloted in 2017, and it was passed, and then published in June of 2018. And then we had some revisions to the bridge design specifications. That was also published in around 2018 timeframe. And then the new ASTM test method that I discussed earlier was published in 2016. And then we just got this past year a new AASHTO standard recommended practice that was developed. And this is a really great practice in that any state Department of Transportation, if they want to find out how long their pipes manufactured with recycled materials will last, can take a pipe and can take some coupons of material from that pipe and follow the methodology I outlined in this service life recommended practice and project how long those pipes will last under their given installation conditions. So that was balloted this last year and published in March of 2019. So now the current M294 standard allows either virgin or recycled materials to be used. The cell classification, which identifies the material properties, are identical for both pipes, M294V and M294R. The NCLS, which is the notched constant ligament stress requirements, are identical for the two pipes. For the pipes manufactured with recycled materials, we require an OIT test, which is an oxidation induction time test, which ensures that those stage 3 chemical failures do not occur. And then we also require an elongation at break test for the M294R pipes, as well as that UCLS test that I mentioned of 34 hours. And then we finally require that for virgin pipes, it's marked as M294V, and for recycled pipes, it's marked at M294R. And that 34-hour test is designed to ensure that those pipes manufactured with recycled materials will last in excess of 100 years at a factored wall stress of 500 psi. And quite frankly, you know, I think the research on this project is extremely robust, but I have great confidence in the M294R projects. I think we have they're from a material performance standpoint, they're even a better material than the M294V products, in my opinion, just because we have incorporated some of these other tests that will further ensure their long-term service life. This is what the standard service life recommended practice looks like. And we in there simply have an equation, which is a fairly easy equation for, although my students might complain about this C factor that they have to calculate to get to the final answer. That said, it's a relatively easy equation where we can simply calculate the time to failure that's required to achieve a given service life at a given service temperature. And it's a fairly straightforward calculation. Statistics are not so straightforward, but that said, that's all rolled into the final calculation as well. All right, so the purpose of the projects was really to evaluate the viability of incorporating post-consumer recycled materials into these pipes for highway drainage applications. And the revisions to M294 were adopted in 2018. And now every state that specifies M294 products can use pipes manufactured with recycled materials. And we really feel it's going to be a game changer, both for the industry as well as for states, because frankly, it's a much more sustainable way to produce and manufacture pipes. And so I think it's something that states will benefit from greatly. We've developed a model that ensures those pipes will last in excess of 100 years, and it's a benefit to the recycling industry as well as to the pipe manufacturers, because they can now use some more materials that they previously were not allowed to use. There's 3 final reports summarizing this, so if you have more interest in reading further, these will be included with the slides and the references available. With that, that concludes my presentation.
That's great. Thank you so much, Michael. That was really fascinating. So I'll ask you please to pass it to Ryan. And a reminder to the audience to keep those questions coming. We have several, but I'm sure that other questions are either already in people's brains or about to be popping up momentarily. So I encourage you to send them along. And with that, Ryan, I look forward to your presentation.
Good afternoon, everyone, and thank you for having me. I'm going to give a quick, brief introduction to what AASHTO is, what the National Transportation Product Evaluation Program is, how that relates to AASHTO, and what NTPEP is doing for the evaluation of M294 material. So without further ado, what is AASHTO? So AASHTO is a nonprofit association founded in 1914. Our members include all 50 state transportation departments. Additionally, Washington, D.C. and Puerto Rico. We also have associate members as well. Our associate members may be federal members, local agencies, other countries such as the Ministries of Transportation in Canada. And AASHTO covers more than just roads and highways. We cover aviation, rail, water, active transport such as cycling. Also, what does AASHTO do for its members? I guess to clarify, when I use the word members, when I'm using members, that is state DOTs. So all 50 state DOTs are members. So when I refer to them as members, I'm referring to those state departments of transportation. We work together to develop transportation solutions. We try to create economic prosperity, enhance the quality of life, and improve safety in our communities, states, and the nation as a whole. We deal in these main sectors here you see on the screen. So we do policy development, advocacy, technical services, leadership development, advancing partnerships, and promoting innovation. Where the National Transportation Product Evaluation Program falls is under the technical services, and we'll get there in a few slides. Real briefly here, I just wanted to put up our leadership. So currently the president of AASHTO is the CEO from the Missouri Department of Transportation, and our vice president is from New Hampshire Department of Transportation. AASHTO is overseen by a board of directors, which is created by each CEO from each Department of Transportation, and they report to our executive director reports to them, and that is Jim Timon. AASHTO also breaks the country up into 4 regions. So in the Northeast, we would be part of the NASHTO group. That is the group that oversees that region. And then when we come together for our national meetings, they represent that, what we call Region 1 or the Northeastern region. Really quickly here, this is a huge org chart, but I just want to give you a real brief, quick understanding of where NEPEP falls. So NEPEP is what we shorten the National Transportation Product Evaluation Program to. It falls under to the Council on Highways and Streets, which then report to the Board of Directors. So what is NTPEP? Like I said a few times now, it stands for National Transportation Product Evaluation Program. This technical service program was founded in 1994, and it reports to the Highways on Council and Streets. The partnership between AASHTO and the member agencies and industry participants. So unlike a lot of AASHTO groups where it's just the state agencies, this one actually has members of both industry and states. We try to combine the professional and physical resources of the AASHTO member departments in order to evaluate materials, products, and devices of common interest for the use in highway and bridge construction. And our primary goal is to provide a cost-effective evaluation for AASHTO members. So, just in some quick bullet points here, we want to simplify the product evaluation process. We want to make it more cost-effective for both the manufacturer and the end user. So, one of the important things here is we don't want the end user, which would be our members of states, to have to evaluate a product from all different manufacturers when it's all the same process. On the same side, we don't want manufacturers to have to ship their product to all 50 states to be evaluated when one evaluation can be done and shared with everybody. We try to reduce duplication of efforts. So along the same lines there, we don't want Ohio to be doing something and then Pennsylvania doing the exact same thing. If we can share those resources, that makes everything a little bit easier. And we also want to serve as a one-stop shop. So we want to make sure that people can come here, they can have their products evaluated here, and the states can log in to the secure website, access the information for not just plastic pipe, but for any of the products we also offer. So it becomes a one-stop shop where they can come in, get the information they need. NEPEP is a technical service program of AASHTO. So as I mentioned before, as a group, we provide some type of service, and that service is product evaluation. So here you'll see a photo of a document. This is what we call SPO1, but it's how our audits are evaluated. So inside this document to be found on our website is the process in which we audit any type of manufacturer. So they could be across any type of product, and these are the quality requirements their quality management system must maintain. So traceability, training, competency, calibrations of equipment, all those things are outlined in here, and that is where our audits basically start off. So basically, there is a desktop review done initially. That is a thorough review of their quality management system. So that follows solely in line with SPO1, which I showed you before. Once that's complete, everything is found to be in order. We conduct an on-site audit. And then once the on-site audit is complete, we work with the manufacturer to resolve any findings we might have had or fix any issues. And then all of that is made available through the NEPEP data mine. The NEPEP data mine is a secure database, which any state DOT with a state email address can gain access to. And you can log in, select the product you want to look at, and you can look at every manufacturer of that product who participates in all their data. Additionally, it's the same side where the manufacturers also submit their applications to be evaluated and put in any initial information. So a quick overview of the audit programs. Like I mentioned before, the manufacturer must follow an established quality control program. The quality control manual should provide the assurance that the products meet the requirements of either AASHTO or ASTM standards, either the NEPEP Technical Committee Work Plan, NEPEP Standard Practice for Audits, which is the SPO1, or a combination of all three of those. The work plans, each individual product has a work plan, and that work plan dials into that specific product. So when SPO1 looks at the over-body quality system, what the work plan does is tie specifically into plastic pipe for recycled material. Here's what you have to do. And then all those are approved and reviewed prior to any on-site audit. During the on-site audit, NEPEP performs an initial audit, and then we come back every year for another audit. The evaluation is of the production and quality control testing. We make sure that what they're saying they do in their quality management system, they are implementing on site. We make sure they have the test reports, equipment calibrations, verifications, that they're doing any required daily checks, they have traceability, and that they can follow all that paperwork. Additionally, our audits are open to any state member. So if you're with any state, our audits are always open door. We notify all our state members of every single audit we're doing, And if you'd like to participate, you can just get in contact with anyone at NTPEP, and we'll just make sure the facility is aware that you're going to be joining our auditor for that audit that day. So a little bit more of what the onset audit includes. So we touch base on document review, but there's also a production inspection. So we'll walk that production line. They'll show us what daily checks they do, what shift checks they do, anything along those lines. There's also a storage yard inspection. So we will go out into the storage yard, and when we're out in the storage yard, we will check for identification, make sure all the markings are correct, make sure that they know when and where this material was made, where it's coming from, it's properly tagged, all those items. We also do a quality control testing evaluation. So we go into the laboratory that is located inside of the production facility, and any tests that they would have to do in that laboratory, either per shift or once per month or whatever it might be, we verify that testing and make sure they're running it in compliance with the correct ASTM or AASHTO specification. And then we also do some testing of products, and we'll get there in a few slides. I'll follow up on the sampling of things we do there. We also do follow-up visits. So if there seems to be a lot of errors or a lot of issues needing addressed, we'll also come back a second time that year to do a follow-up and take some new samples and retest, and then we can show both reports to our members and they can see the progress they've made. And there's also surveillance audits. So anyone in the program, a DOT could see a report. NTPEP, we're not certifying or approving products. We're just providing that data for the states to make an acceptance decision. So in this surveillance type visit, a state could see some issues they think are issues with them. They would choose to come back out and pull some more material or walk through the yard or anything along those lines. So for our annual testing of products, random product samples are tested for conformance during the audit. So we select those at random, and we have the mill ship them to the NTPEP designated laboratory. So here at AASHTO, we're just an office building. We don't have any test facilities. So we actually contract with two different laboratories for plastic pipe, and the manufacturer will then ship their material that's randomly selected by our auditor to that facility for testing. And then, like we mentioned in the last slide, there could be follow-up audits or surveillance audits in the states in that period if they'd like. And then test results are posted on our secure area, which is the NTPEP data mine website, which any registered state user can have access to. So we post the results there as well. Resolution. All of this is on the burden of the manufacturer. So it's their job to identify the cause of the issue, to correct the issue, to document the resolution, and revise the quality management system if they have to. The important thing here is that we're getting to the root cause. We don't suggest any types of corrections. We just point out the issues, and it becomes the burden of the manufacturer to resolve that. Another way some manufacturers choose to do some additional testing to validate results, we can do a round robin or things like those to try to look into why an issue is occurring. We also do corrective action reports. So each manufacturer is given a corrective action report based on any findings they have. They are given a period of time to fill that out, and they submit that, and it's also posted into our secure site so that any state can see each issue they had during the audit and how those issues were resolved and determine if they meet the needs of their state. All right. So the NTPEP audit program for thermoplastic pipe, all of our audits are conducted in accordance with AASHTO M294. So starting about mid-year 2018, we started to allow for recycled material to be used in our audits for NTPEP. Those were basically the end of 2018 when the spec was released. And then in 2019, this whole year, we've been evaluating this recycled material along with the virgin M294. So what are some specific QMS stuff that kind of goes with the thermoplastic pipe program? They have to have traceability of all their materials from the raw to the finished pipe. So we make sure they're able to trace it. We make sure there's no way that they are crossing any type of virgin with recycled and everything's properly labeled. In the next bullet point here, we have to make sure that they're able to track all their reports, all their test mill reports are tracked and traceable. And there's a written procedure for labeling and storage of their finished products. So when the auditor's on site, we'll go out to the yard and we'll randomly select a few different pipes that were made on different days, different shifts within the last year. And then we'll trace all that material all the way back to the resin that initially came in at that facility, either a virgin resin or in the M294R case, a recycled resin. So once we go through all that and we trace it all back, the auditor also selects a few different pieces of material to be tested. So if a M294R material is selected, all the tests you see on the screen would be tested for at our third-party lab. Additionally, the manufacturer would also run those same tests on their product as well. They'll submit the data to us, and our third-party lab will also submit the data to us. What we provide the states with is what we call a comparison test report. So the comparison test report shows the data from the NTPEP designated lab directly alongside the data from the manufacturer. The states can look at that and see if the numbers are similar, if there's any variation. It also allows us to see if maybe a piece of equipment may have went out, or if someone might be running the spec incorrectly, because you'll start to see they might meet the minimum, but they vary a lot from their private lab that is also running to the spec. So that's the final report that we issue along with the audit report that gets uploaded to DataMine. As you'll see in the bottom right-hand side, the 4 tests, OIT, elongation at break, density, melt index, and UCLS are all in red. The reason those are in red is because these are finished pipe tests that are not required for virgin pipe, but are required for recycled pipe. So there's a little bit extra testing, which causes the cost testing to go up slightly for the recycled material. Once all the corrective actions are made, all the pipe meets the minimum specification outlined in AASHTO M294R. The quality manual is updated. It meets the requirements in the most current version of the SPO1 document that we use. The final thing we issue on DataMine is a compliance authentication document. So this document is given to each facility. It indicates that they're compliant with the Thermoplastic Pipe Technical Committee work plan for the year. These documents can be downloaded. Some states require these to be submitted to them. What I always tell everyone is just because you have a document doesn't mean they're compliant. Make sure you're reading their reports, you're checking the corrective actions, make sure you're doing your due diligence to make sure, even if they resolve the corrective action, that it meets the needs in your state as well. So that's pretty much a really quick, brief overview of the National Transportation Product Evaluation Program and how we handle plastic pipe. Here's my contact information. At the end here, we'll have some more time for questions, but I'm going to turn it over to Joe.
Great. Thanks, Ryan. That was great. And there are a lot of very interesting questions coming in that I'm being delighted by. But encourage people to keep sending them. And Joe, we look forward to your presentation.
All right. Let's see if I can get this up here. Okay. Hopefully everyone can see my screen. Thank you, everyone. I'm excited about being on. I think my last presentation is a great segue. Taking from the previous 2 presentations, Michael Plumier spoke about the research that went into developing and changing the AASHTO specification for corrugated HDPE pipe. Ryan's presentation was about the quality control program that basically governs this product as well. And finally, I'm going to talk about from the manufacturer's perspective how we ensure that we are meeting those quality requirements. Because I think both Michael and Ryan touched on briefly, is that this by any means, this is not a product that has any lesser of quality control program or material requirements that would be if it was made out of straight virgin pipe. So as a manufacturer, we still have to hit those same quality control guidelines that we would have to hit if we were making this pipe out of 100% virgin material. One thing as engineers, I think and I'm an engineer by education and by trade, is that we're typically very good at making observations, designing solutions, but one thing that we're sometimes poor at is explaining why. And one thing that I always like to point out is the research, and there was 2 NCHRP projects over the course of 10 or 11 years that went into making these changes into the AASHTO specification. That research was largely funded by state DOTs. It wasn't manufacturer funded. It wasn't privately funded. That was funded through NCHRP projects, which ultimately get funded through state DOTs. And so there was a great interest out in the marketplace in looking at this. And this is one of the reasons why is ASC, so the American Society of Civil Engineers, every 4 years puts out a report card. And it kind of gives a letter grade to America's infrastructure. And they grade America's infrastructure as a D+. And as many of you know, engineers are under many of the same constraints that others are, where our needs are growing. In many cases, they're growing exponentially, but the available funding to fulfill those needs is either flat or growing very slightly. And there needs to be big ideas and research done to help bridge that gap between our needs and our available funding. And I feel like this research and this program is a great example of what we can do as an industry and as government employees and owners to help solve that ASC grant challenge of really meeting those infrastructure needs with new innovative ideas. For example, the bottom right-hand corner, that photo is a 60-inch culvert made out of recycled material that's underneath a state highway in Ohio, and it was made out of recycled material. The picture above that is a bale of recycled material that comes that literally was taken at one of ADS's post-consumer recycling facilities. Again, so we're taking items, products, single-use plastics that maybe at most have a 6-month service life, and we're turning those into literally turning them into a product that's going to last over 100 years. So I think it's something that everyone can be proud of. ADS, and it may be a surprise to some on the call, ADS has, we call it our Green Line Polymers division, so a solely owned subsidiary of ADS, that we have 8 domestic recycling facilities, and annually we recycle over 400 million pounds of HDPE every year. So it's a great story. In many cases, those curbside recycled plastics, so those Tide bottles, milk jugs that you're putting on the curb every week, get made into a corrugated HDPE plastic pipe and gets put under the curb, so to speak, as drainage pipe later on down the road. So it's a good sustainability story. It's a good story about the circular economy. Again, taking household items that by other means would be make into a landfill and making products, long-lasting products out of them. Again, part of ADS's story about our kind of product evolution, kind of the bottom right-hand statistic is, about 13, 14 years ago, ADS was only using about 24% of our products were made out of recycled material. Kind of flipping the switch, moving ahead to over 13 years, that instead of 24%, we're all the way up to 57%, and I would see that number to grow as we move forward, especially with the addition of this new AASHTO M294 recycled standard. Why is drainage pipe the ideal outlet for some of these recycled materials? In many cases, it's very simple. We can take really any kind of colored flake that gets put on the curb, mainly because our end product is black. Some of you may not know that polyethylene in its virgin form is actually a white opaque color. ADS and other HDPE pipe manufacturers actually add carbon black to that to make the product black. We do that in order to increase the UV resistance of the product. So again, it's kind of twofold why we add that carbon black. First off, we're able to take recycled materials made from all different kinds of colors, and when we make that black by adding carbon black, it actually enhances the UV properties of our pipe when we use it in the field. We're also Dr. Plumier touched on it a little bit in his presentation. The AASHTO M294 recycled specification is truly kind of what we call a performance-based specification. So it's very heavy on quality control testing once the product is made, but we are allowed to blend different materials, a wide range of materials, in order to make that product. And this is largely what my presentation is going to be focused on, and how ADS responsibly blends a wide variety of sources to make a product that meets the AASHTO standard. A couple of other things that makes pipe the perfect outlet: odors. This pipe is largely being used in private and public stormwater applications. If there's a very small odor on the pipe after it's made, it's not a huge concern. We're literally taking single-use plastics that have a very short service life and making a product that has a service life of over 100 years. There's kind of unofficially, ADS estimates that about 25% of all pigmented HDPE that's curbside recycled actually makes it back into our drainage products every year. So again, just some powerful statistics when we talk about the scale of how much of that post-consumer curbside recycled material is actually making back into our corrugated HDPE product. As I get going here into the research project that ADS pursued, it's basically about material property variability. How can ADS ensure as a manufacturer that when we're using post-consumer recycled material, we're using post-industrial recycled material, and we're using, in some cases, virgin material, blending those items together to make sure that we're making a pipe that meets the AASHTO standards and is going to last 100 years. And ADS puts an inordinate time of effort into making sure that we're making a great product that meets all the quality control standards. And we're going to kind of go into a little tutorial and show you how we do it. Just to talk about some nomenclature as we move forward, when I say post-consumer HDPE material, that's, again, general public curbside recycled material. We're talking milk jugs, Tide bottles, Tropicana bottles, detergent, all those items. It typically just includes some commercial and industrial products that have served its final purpose. When I start talking about post-industrial HDPE, these are a lot of times excess or rejected bottles from different manufacturers. It might be bottles, crates, drums, dunnage, things that typically aren't used by consumers, but they might be reject parts from different manufacturers. So that's what when I say post-industrial HDPE, that's largely what I'm talking about. When I start talking about flake, so when ADS, we have 8 domestic recycling facilities, when we purchase HDPE material, it comes to us in bales. So those post-consumer plastics are still largely in their original form, whether they're Tide bottles, milk jugs, whatever they are. ADS then processes that material. So we literally take it, we sort it, we wash it, we shred it, we dry it, we wash it again, and after we get done processing processing it, it is what we call flake. So there's a good photo of what we consider flake. Again, that's that kind of the shredded up post-consumer or post-industrial recycled material. When I say salt and pepper blending, and part of the research that AASHTO in the project is how we looked at what salt and pepper blending can do to your overall performance, homogenized performance of your material blend. So that's taking two different types of flakes, whether it's a post-industrial flake or a post-consumer flake, and blending them together to make kind of a homogeneous mixture of flake. And then finally, and Michael had a nice photo of this in his presentation. I think this is maybe the same photo, pellets and pelletizing. So after ADS processes that post-industrial or post-consumer recycled material, we have it in its flake form. And before we make out a pipe or make it into pipe, for the most part, we then make that flake into pellets. And one of the big reasons, or there's two large reasons why we make that flake into pellets before we pelletize the pipe. One is increased homogenization of that material. So again, when we take that flake, whether it's from post-industrial or post-consumer, we then homogenize it by making it into pellets. What we also do is one of the largest contaminants we have when we're making HDPE pipe happens to be polypropylene. And the reason for that is many of your that you recycle day in, day out, whether they're milk jugs or Tide bottles, the bottle itself, the jug itself is made out of polyethylene. The cap is made out of polypropylene. And it's very, very difficult for us to hand sort those caps away from the jugs. One way that we're able to do that is after we process that material, we then melt it. And since polypropylene and polyethylene melt at different temperatures, we are then able to melt filter out that polypropylene and then make that polyethylene that passes through that filter into pellets and just to make good pipe out of it. So the way ADS looked at this experiment, this study, was to kind of track how our as different raw material streams, as we went through the process of making finished pipe, how our raw material properties varied at each step of the way. So and you're going to see the data as we go forward. But again, here's looking at kind of the flow chart. So we had raw materials come in, whether it's post-consumer or post-industrial. We then took those raw materials and did material testing on it. Now, we have a whole batch of raw material testing that was published with this report. In this specific presentation, I'm only going to focus on two, and it was the same two items that Dr. Plumier introduced in his presentation. It was both the NCLS test and the UCLS test. So again, if you remember, the NCLS stands for Notched Constant Ligament Stress Test. UCLS is the Unnotched Constant Ligament Stress Test. So again, we're looking at those stage 2 failures through stress cracking that ADS, or not ADS, that HDPE is prone to, and we're trying to look at are we hitting the minimum values, the stress crack values that is required under the AASHTO specification, and B, when we're looking at the UCLS test, is to make sure that we're not getting any contaminants in our pipe through our processing of our post-industrial and post-consumer recycled material. So as it runs through a raw material stream, we're taking samples of the raw material, we're salt and pepper blending it, taking another sample, we're pelletizing it, taking another sample, and then we're making it to finish pipe production, and obviously sampling those items as well to make sure that we're hitting the requirements that are needed with the AASHTO specification. The study looked at 45,000 pounds of total material. It kind of broke down this way, where we looked at 45% of this total 45,000 pounds was post-industrial flake, 25% was post-consumer flake, 15% was post-industrial blow molding flake, 10% post-industrial film, and 5% post-industrial pellet. We actually made 2 separate pipe types out of this. So much of, if not all of the presentations on this webinar were focused around the AASHTO M294R product. There's also another recycled pipe product that there's currently a specification out there. Now, that product is not for public applications. It's geared more to private land drainage applications. So you're looking at either agricultural applications or private stormwater, like a McDonald's or Chick-fil-A is where ASTM F2648 is used. But we looked at both different pipe types as we were doing this experiment. I'm not going to get into the nitty-gritty of both tests we looked at. So I think Michael had a similar slide on the NCLS test, but the NCLS test basically looks at the stress crack resistance of HDPE, and the UCLS test that looks at the stress crack resistance and the crack propagation time due to a presence of a contaminant. Here's the results. Some things that I think it's wise to point out. So when we're looking at our different raw material streams, you're looking at the bottom left-hand corner, that the 6 is down the bottom left-hand corner is indicative. That would be post-consumer recycled material. As you can see, it's a rather poor performing material. When you're looking at stress crack resistance, the 2 red lines on that chart that are going horizontal, those are the minimum values that are required for both the ASTM F2648 product and the AASHTO M294R product. If you're looking at those 2 lines, AASHTO M294 actually requires a higher NCLS value, so that's why one line's above the other. But as you can see, that the post-consumer recycled material is actually a fairly poor performing raw material when you're looking at NCLS. The one nice thing about it is that it's consistently poor performing. So as we're bringing in raw material streams, specifically post-consumer recycled material, we have a pretty good idea what it's going to be. It's going to be rather poor performing, but it's consistently poor performing. And in knowing that, we can then blend different raw material streams, whether it's a very good recycled post-industrial material or other virgin materials to help make up for that poor performing stress crack resistance. Again, kind of a rather similar story when you're looking at NCLS or UCLS and those different raw material streams. That 6 material is the post-consumer recycled material. Then comparing that to the post-industrial flake films, you could tell it's kind of by and large a poor performing material. But as we move it through our raw material streams, so that SP material at the bottom, that would be that's basically a salt and pepper blended homogenized material. So again, that was material that was among all those raw material streams that was homogenized by mechanical means. So you can see there's a pretty large bump in performance in the UCLS just by salt and pepper blending all of those raw material streams, and we get another fairly sizable bump in performance when we pelletize that material. So that's the NP column, and then as we make it into pipe, into both F2648 product and M294 pipe product, the performance, the material performance in the UCLS test increases even more. So again, when we're looking at the significance of pelletizing to variability, when we're taking our raw material streams, it helps if we salt and pepper blend, but it actually helps even more if we pelletize that material. So that's why you say that when Dr. Plumier spoke about pelletized material, how if you really wanted to, you could make pipe out of flake, but in reality, you really shouldn't make that M294 product out of flake. It's better to make it out of pelletized material because you get a more consistent result. Just kind of conclusions of the study. Raw material testing alone does not predict final product performance. So again, there's several different blends that go into making a finished product. That's why it's important the specifications are around kind of what Dr. Plumier called a performance-based specification. Mechanical blending, so that salt and pepper blending facilitates homogenizing the material. And you get a statistically significant reduction in variability with pelletizing salt and pepper and by melting it down and making a pellet out of it. So also, along in the process, we saw a significant increase in stress crack resistance. So both NCLS and UCLS, when we added a high molecular weight virgin material in the blend to meet the AASHTO M294 specification requirements. Hold on here. I think my computer just froze, but I more or less that was my last slide. So Lynn, if should I throw it back to you?
Great, thank you so much. And Joe, you can stay there or you can make me the presenter, either one. So we've had some great questions, and I think you are all unmuted, speakers, you are all unmuted. So I want to give you a chance to answer them. And I'm gonna, there's a number of questions about possible applications for these pipes, but there's also two that relate to price. And I wanted to start with those. So somebody who I'm going to guess is a recycling coordinator, I don't know this for a fact, wanted to know if they might enjoy a discount on purchasing a pipe, and Joe, they didn't say this, but I'm going to play this out as if they were buying it from ADS, if they were able to sell you their baled HDPE. So could they do kind of an actual closed loop system with their material coming to you and then having value from that and buying pipes at a discounted rate?
I would be happy to speak to that individual offline, but when you're talking about price of pipe, that's a way above my pay grade, so to speak.
Okay. Well, I will be sure you two are connected with each other. And then there were a couple of questions about, is there a real price comparison between, we're not asking for actual price, but just proportional, between the pipe that are M294V as opposed to M294R. And I think that probably several of you could chime in on that. Are we seeing a real price differential there?
So I'll try to hit it first. Typically the prices are very similar, if not the same, and I'll give the reasons for that. First off, as a manufacturer, we have to do, even though the final material properties and pipe properties of the finished product are exactly the same, ADS and other manufacturers have to do a whole lot more quality control testing on the recycled product than they have to do the virgin. So that's one part of it. And the other part of it is where ADS and I think others see the real benefit of this specification change. Well, two things. First off, it makes it a much more sustainable product, which I think everybody wins and is thankful for. Second, it allows us to have more consistent raw material streams. So, just like everybody else, when a hurricane hits the southeastern part of the United States, whether it's Houston, where a lot of the petrochemical companies are based out of, we see those same disruptions with our raw material streams that you might see, with the gas you put in your car. So it's a more sustainable product, and from a manufacturer's perspective, I think it largely it allows us to have a more consistent raw material stream.
Great. Ryan or Michael, do you want to chime in on that one?
Yeah, I don't really have much to add that from what Joe had already indicated, other than it is a pretty variable thing, and there are some states that we see that are wanting or interested in paying a premium for materials manufactured with recycled content just because of the benefit from a sustainability standpoint. And so I think we're going to continue to see some fluctuations with regards to that and some ebbs and flows with regards to pricing.
Great, thanks. So questions about different applications, I'm going to sort of bundle these into one question. Could you use these pipes for leachate out of landfills? Would it be suitable for, I just totally lost that picture. Long-term treatment systems used in the soil and groundwater cleanup industry? And is this comparable in any way to smooth pipes?
I can take a first shot at it, and then Joe can add to this since he has a lot of the applications from advanced drainage system side. But yes, certainly for mining leachate applications, there's a lot of corrugated pipes used in those applications right now. In fact, a lot of them that can contain recycled content. So that certainly would be an application, as it would be the water treatment ones and the any type of treatment applications. As far as the comparison to solid wall pipes, they're both polyethylene. The grade of materials in a corrugated pipe for drainage applications is a little bit lower with regards to stress crack resistance than the solid wall pipe applications. And the reason for that is that the solid wall pipes are under higher internal pressures, and so they have to use a more pressure based material. So, but that said, they're both made out of polyethylene, and in fact, some of the grades that we use now in the corrugated pipe industry are similar grades of materials that were used decades ago in the solid wall industry. So we're seeing some evolution there as well. Joe, you have anything to add?
Not much, other than, again, I think you hit it, but the research was focused on gravity flow drainage rather than pressure pipe.
Okay, great. So a couple of questions about NPDES designated states and whether we can anticipate EPA mandating the use of these PCR pipes as part of the NPDES system, and if not, what possible incentives or initiatives could we use to make that happen?
I'll probably defer that question to Joe first. I mean, I think it's a good thought. I'm not aware of any initiatives right now that are underway that would make that happen. That said, I think as we continue to progress as a society, and certainly in North America, we've got some great needs here and great needs to do things on a more sustainable basis. So I think that there could be some opportunities, but I'm not aware of anything right now with regards to either any requirements from the EPA or from NTPEP that's going to dictate or mandate these pipes. But Joe, do you have anything?
No, I don't. I think you hit it pretty well, Michael. Lynn and the group, I mean, the use of recycled plastic, recycled corrugated HDPE pipe in public and private storm drainage is largely regulated by state DOTs, counties, and municipal governments. So when we're looking at the increased use of these products, at least from ADS perspective, that's where our primary focus is when we're trying to get the product approved and used in more places.
I will add just quickly too that we're seeing some evolution, or I'm seeing some evolution as somebody that's been in this industry for a long time. I think attitudes are shifting and things are changing, and I see it particularly at the university level as a professor. Students are wanting to make a difference. They're wanting to do things more responsibly than what was done in the past. They're seeing issues that were created by our past behaviors as a society, and even as in our choices of engineering materials. So I think we have great opportunities, and we have a new generation of engineers that are coming through that are going to help make a difference, and this could be a very significant part of that. So I'm encouraged by that. That said, I think we still have there's a lot of people out there yet that don't acknowledge and don't really fully understand the significance of the problem right now that we're facing. So I think we've got some good news there, but we still have education that needs to be done.
Great. So here is a wonderful New England-centric, well, perhaps not, I think it's New England-centric. Could you accept maple tubing mainline as an input? It's HDPE. It would taste good.
Can you repeat the question?
So when you collect maple syrup, more and more people are using these plastic feeder lines. They put one tap and it's a gravity thing, and it goes to the next drainage section and it runs all the way down. So what happens is that you end up with miles and miles and miles of these plastic tubes that are made of HDPE that don't last forever and need to be recycled. Could that be part of the feedstock?
Gotcha. Go ahead, Joe.
I was going to say, as long as it's made of HDPE, I think we can make a make a crack at it.
Even if it tastes good.
Yeah.
Your plants would smell great, Joe.
There you go. Great. And so somebody comments, I saw that the OIT requirements were referenced, but results weren't shared. How common is it to fail minimum OIT requirements?
Right. There's two types of what we call thermal stability tests for these pipes to ensure that they don't oxidize and don't fail prematurely over time. And the first is what's just called a thermal stability test, and that's been in the standard for decades. And it's basically you just heat up the material to a certain temperature and wait for it to oxidize. And you actually heat it up in increments, and it has to get to a certain temperature before oxidation can occur. So that test is still in there, and it has been in there, like I said, for decades. We added an OIT test, which is a similar test, but it's done a little bit differently as an additional check, just to make sure that after reprocessing these materials multiple times, it can be possible that you're going to use up some of those antioxidants that were present in the material beforehand. And so if it goes through multiple heat histories, we wanted to make sure that manufacturers would add some type of antioxidant package to further stabilize it. And 20 minutes was just shown as historically a good number to demonstrate that you have adequate antioxidant to ensure your long-term service. So we didn't show data there, but that's because, frankly, we put the 20-minute OIT requirement in, and all of the pipes that we tested didn't have that requirement in. And so every pipe that I showed that was in that table was, in essence, not manufactured to this specification and did not have 20 minutes. That's why we added the 20-minute requirement.
Great, thank you. And Ryan, I think this question is for you. This caught my eye as well. You talked about the requirement for material traceability when you're doing the audit. So how far back in the chain of custody does that go?
So for us, it goes back to the resin. So as long as you have the test reports for that resin that you brought in, then that's what we're looking for. So we want to make sure it can come back to whatever rail car it came in on, or however it came into the facility that way. If it's recycled, it's a little different because some facilities are pelletizing themselves, but as long as they have test reports for that, that's all they need.
Okay, so it's not literally, gee, it came from Lynn's transfer station. It's that it came to you in this particular lot, and this lot was tested, and here are the test results.
Yeah, so we know the manufacturer of that resin.
Okay, great. And one final question, please. Is there a limit to the burial depth of HDPE? So can you make it thick enough that it would compete with RCP burial depth? I don't know what RCP burial depth is, but I bet somebody there does.
Yeah, this is an interesting question and a common misconception, I believe, about plastic pipes. In general, a plastic pipe, regardless of the wall thickness, can be buried actually typically many times a lot deeper than a reinforced concrete pipe, and that's because the pipe interacts with the soil around the pipe around it to form its structure. So pipes can be buried very deeply if installed properly under standard installation conditions. All the pipe manufacturers can provide cover height tables as to how deeply the pipes can be buried. But basically, this corrugated recycled pipe can be installed to the same depth as the pipe manufacturer with virgin materials, and those cover heights are going to be dependent upon the quality of the installation. And again, both the Plastics Pipe Institute as well as the pipe manufacturers can supply cover height tables.
Wow, and you knew what that meant. Excellent. Well, thank you, everybody, to all the speakers. Great and fascinating presentations. I learned a great deal, as I'm sure did the audience. And thank you also to our audience for participating and for asking questions. Really appreciate it. As a reminder, the recording will be posted. The PowerPoint presentations will be posted. And if you have any follow-up questions, feel free to email me at lynn@nerc.org, and we'll be sure to help you out. So again, thank you to everybody and to APR for co-sponsoring, and have a great rest of your afternoon, everybody. Bye-bye.